In this set of notes, we're going to look at inference for logistic regression. So it's an important distinction between linear and logistic regression is that the regression coefficients in the logistic regression are not terribly meaningful on their own. So let's compare the interpretation of the coefficients for linear and logistic regression. So in linear regression, a coefficient informs us of the expected change in the response variable for a 1-unit increase in the explanatory variable. And of course, that's with all others hold constant. And typically we're thinking of an additive model here. In logistic regression, a coefficient informs us of the expected change in the log of the odds of the response variable for a 1-unit increase in the explanatory variable, with all others held constant. And again, thinking of an additive model. So the interpretation of the linear regression coefficients is much easier to understand. So for this reason, when the outcomes are categorical, it's much easier to think about the outcome in terms of probabilities and odds ratios. These are the quantities that are usually reported and described in an analysis rather than the regression coefficients themselves. So in this note set, we're going to look at estimating and constructing confidence intervals and carrying out hypothesis tests for these quantities. So we're going to start out by looking at inferences for the probabilities, and here we've denoted them as pi. So we've already talked about the estimation of probabilities based on the fit of a logistic regression model. So given a vector of explanatory variable x, what we do is we calculate the linear predictor, so we get those estimates, and then we in turn estimate the probability based on this piece right here, and that's what we did last time. And so it should be noted that since the maximum likelihood estimates are invariant under transformation, pi hat may also be considered the maximum likelihood estimator of pi. So let's talk about constructing confidence intervals for probabilities. It ends up that the construction of confidence intervals are very similar to what we've seen before. So in module 4.2, we had the following results, where SE hat was the square root of the following. And it ends up we can use this distribution to help us calculate confidence intervals as well as hypothesis test. And so we can construct confidence intervals for nu as follows. And so notice here, you've got your typical format of a confidence interval that you're used to seeing. What we've got here is we've got the estimate, and then depending on if we're looking at the lower or the upper endpoint, we've got minus or plus. Then right here, we've got that critical value that comes from our distributional assumption, and we've already shown that we have approximate normality here, so that's why we're going to use that z. And then we have the standard error of the estimate. So this is your typical form of confidence intervals that you're used to. And then what we can do is to find a 1 minus alpha confidence interval for pi. We can then do this transformation, where here L stands for the lower endpoint of the confidence interval, and U stands for the upper limit of the confidence interval. So in other words, a 95% confidence interval for logit pi for a fixed value, let's say at x equals to x naught, a single predictor variable is the following. Oops. So we're going to have a beta hat naught plus a beta hat 1 x naught. So notice this whole piece here, that is the new hat, plus or minus 1.96, which is the critical value for a 95% confidence interval when we have that normality assumption, times the standard error. And then substituting each endpoint into the inverse transformation will give the corresponding interval to estimate pi. And so notice the reason that we have to pick a fixed value of x here is because we're not trying to estimate the coefficients, we're creating a confidence interval to estimate pi. And so that's an important distinction here. So we could also construct hypothesis tests for probabilities. So in principle, you could carry out this hypothesis test where you were testing to see if pi was equal to some value under the null hypothesis. And so based on this, you would need to calculate nu under that null hypothesis. And then really we would carry out this test using this distribution. But however, in practice, it's quite rare that we would actually have a hypothesis test about a specific subject that you were interested in testing. Because notice, in order to calculate this, the reason that we need a specific type of subject is since really this is a hypothesis test about pi or nu, you would have to specify that x is equal to x naught. So you would be performing a hypothesis test for pi at a specific set of explanatory variables, or in other words, a specific type of subject. So that's why we don't typically do this. So let's talk a little bit about limitations of estimating probabilities. Probabilities have the advantage that they are particularly easy to interpret. However, working with probabilities is inconvenient for logistic regression in many ways. Notice that the model is not linear in probability. So suppose that beta j is equal to 1 and xj changes by 1. How is that going to affect the probability? So notice this is similar to what we talked about in linear regression, and we saw this last time, where we're going to increase x by 1 and see what happens to our estimate. And it ends up that a fixed change in x often has less impact when a probability is close to 0 or 1 than when it's close to a half. And so let's look at an example. Suppose we started out at 50%. We're going to show that it would go up to 73%, but if we start at 90, it's going to go up to 96. So let's see why this is true. So we're going to start with nu hat is equal to beta hat naught plus x. So what we're assuming here is that we're going to just work with simple or just a single explanatory variable. And the reason I've written it this way is we're further supposing that beta j is equal to 1. So that's why the beta 1 here is gone, because it's just equal to 1. So, and pi hat is equal to e to the nu hat divided by 1 plus e to the nu hat. And what we're going to do is we're going to increase x by 1. So in other words, what I'm saying here is nu hat nu is equal to nu hat plus 1. So again, this is very similar to what we would do when we worked with linear regression. We would look at y hat, and then we would look at y hat nu and see how those differed when we increased by x1, or increased x by 1. So this is a very similar, it's just we've simplified it even further by setting beta 1 equal to 1. So notice, again, we've got nu hat nu is really equal to nu hat plus 1, and pi hat nu is equal to e to the nu hat plus 1 over 1 plus e to the nu hat plus 1. Okay? And it ends up that with some algebra you can show the following. I'm not going to go through it here, but if you just play around with the two values, you can show that pi hat nu is equal to pi hat times 1 plus e to the nu hat divided by e to the minus 1 plus e to the nu hat. Okay. So again, very similar to when we would have y hat and y hat nu, and we would show that y hat nu is equal to y hat plus something. Okay. So if pi hat is equal to 0.5, then nu hat would be equal to the log of 0.5 over 1 minus 0.5, but notice that's just equal to the log of 1, which is 0. So we can now calculate pi hat nu. So pi hat nu would be equal to 0.5 times 1 plus 1 over e to the minus 1 plus 1, which is equal to 0.73. So if we start out, we're just going to increase x by 1. So this is about as simple a case as we can get. We can see that if we start out with pi as 0.5, we increase x by 1, pi hat nu is going to be 0.73. But what if pi hat was equal to 0.9? Well, in this case, we're going to end up with nu hat is equal to the log of 0.9 over 1 minus 0.9, which ends up being equal to 2.1972. And then pi hat nu is equal to 0.9 times 1 plus e to the 2.1972 divided by e to the minus 1 plus e to the 2.1972, which is equal to 0.96. So we see when we start out with a pi close to 0.5, we see a much bigger increase than when we start out with pi equal to 0.9. And you would see something very similar if you had 0.1 there instead. And so this is what we're talking about up here at the top, that even though we're making a fixed change in x, that impact is going to depend on the starting value of pi. It's not linear. So another way of putting this is that in order to calculate the change in probability as one explanatory variable changes, you have to specify all the explanatory variables. And this complicates when lots of variables are present, and the most attractive feature of an additive model, in other words, the ability to describe what happens when you change one thing and leave the rest the same, you don't really get that anymore. And so this has particularly important consequences for what are called case control studies. So let's look at logistic regression and case control studies. The purpose of a case control study is to assess the magnitude of the association between an exposure and a specific disease or health-related event. And so the simplest design for a case control study is composed of two groups of subjects. Subjects newly diagnosed with the disease of interest, called the cases, and subjects without the disease of interest, also called the controls. Once these are identified, the prevalence of exposure to a certain factor is measured and compared. So case control studies are a type of retrospective sampling. And so notice in retrospective sampling, it's different than what we typically work with. In a retrospective sample, the explanatory variable x is random rather than the response y. And the reason for this is, think about how the cases are identified. When we think of the disease or the outcome of interest, we first identify those people, place them into cases and controls, and then for all the cases and controls, see whether or not they had the exposure. So this is why in these retrospective samples, we end up with x random rather than the response y. So in case control studies, it ends up that the maximum likelihood estimates, as well as their approximate sampling distributions, are equivalent to that obtained from the logistic regression model under the assumptions that the model is correct and the selection of cases and controls is independent of the explanatory variables. Now, the assumption that the selection of cases and controls is independent of the explanatory variable is actually a pretty big assumption, and that's going to be often violated in case control studies. And so it ends up that this is going to be a major source of bias. So for example, case control studies often have found links between childhood leukemia and exposure to electromagnetic fields. However, subsequent investigations have indicated that this is due entirely to case control bias. Families in low socioeconomic status are more likely to live near electromagnetic fields. Families with low socioeconomic status are also less likely to participate in studies as controls. And so socioeconomic status does not affect the participation of the cases. However, cases are usually eager to participate. So this results in a spurious association between EMF and leukemia. So let's talk about the intercept. Another important thing to note from the preceding theorem is that it makes no claim about beta hat naught. And this is because the case control sampling affects the likelihood with respect to beta naught, as the sampling probabilities are absorbed into the intercept. And so what you find out is that when you have a case control, beta naught is really going to be beta naught from the random sample plus the log of tau 1 and tau naught, where these are the selection probabilities for the cases and the controls retrospectively. And I just saw a mistake here. I will fix this in your copy. This denominator should be a tau naught. So in the usual situation where we intentionally oversample cases, this leads to an overestimation of beta naught. So thus, it's not possible to estimate beta naught that describes the general population unless we know tau 1 and tau naught, and therefore not possible to estimate the probabilities either. And you're going to look a little bit more of an example of this in your homework. All right, so next let's talk about odds ratios. Given that the regression coefficients are difficult to interpret, but the estimation of probabilities has a number of drawbacks, how should we summarize and report our model? It turns out that odds ratios provide a readily interpretable and easily to estimate a compromise without any of the drawbacks of estimating probabilities. So estimation of the odds ratio. Note that the odds of an event occurring for a subject with a vector of explanatory variables x is given as follows. Thus, the odds ratio for comparing two subjects, one with explanatory variables x1 and the other with explanatory values x2, is given as follows. In particular, consider the odds ratio for what happens when xj changes by amount delta j, while the rest of the explanatory variables remain the same. Well, you end up with the odds ratio is equal to e to the delta j beta j. And this is exactly what we need. All the other variables vanish and our estimate depends only on the beta j and the change in xj. Therefore, we can estimate this odds ratio as well as carry out inference based entirely on beta j, and we don't even need to be able to estimate beta naught. So we can apply these results to case control studies. So let's look at an example. So last time, or in the last module, we looked at the Donner Party example. We're going to continue that. So we could ask, for example, what is the odds ratio for a member of the Donner family failing to survive the winter with a 10-year increase in age? So recall from the R coding section, the previous model, we could fit the following. So here we're going to fit survived as a function of age and female. So when we do this, notice that male is the base case. So here we have our output. And the model was fit with survival as the outcome. So here we want to fail to survive, so the estimate is now going to be positive. So what do we mean by that? If we look here at our age, we have age right here. And again, this was modeling survival, but we want fail to survive. So in this case, we can just change the sign on the estimate. And then, looking at our estimate here, we can multiply this by 10 because we want the 10-year survival rate. Now, notice that this is going to give our estimates for males. And the reason for this is male is our base case here. And so since male is the base case, this model is fit where if sex was equal to 0, or female would be 0, we would end up losing the female in the interaction term. So that's why the age here, or this odds ratios, is just for the males. Now, what if we wanted to get that estimate for the females? To get the estimate for the females, we would have to account for the interaction. So again, this model was fit with survival as the outcome, and we want fail to survive. So we have the effect of age for females as the following. So we start out here with the model. Everywhere we have female, we're going to plug in 1. So you'll see that here. And then we can combine the terms so that these two are not multiplied by age and these two are. So we end up with an estimated effect of the following. So notice here, if we want the effect just on age, we're going to have beta 1. And again, we fit survival. So for beta 1, we're going to use the positive. So you see that right here. And then for beta 3, again, we're going to change it positive because we modeled survival, but we want fail to survive. So we have to flip those signs in those estimates. So adding those together, we get 0.1941, and we get the following odds ratio. So note that these odds ratios apply to any 10-year difference. So it could be 50 to 40, 30 to 20, etc., due to the linearity of the assumption. And so this goes back to this idea of we always want to be very careful of the model that we fit. So for example, if you were to go through here and the only thing that you changed was instead of survived, you changed this to died, you would actually find the exact same estimates that we got here, except we wouldn't have to worry about changing the signs from the output. All right, so let's talk about confidence intervals for odds ratios. As with probabilities, confidence intervals for odds ratios can be obtained by first obtaining confidence intervals in terms of beta hat and then transforming. So remember again, we fit these 4 different models in module 5.1. So here are those 4 different models. And then to get the confidence intervals in R, you would use the confident.default function. Now we're going to spend a lot of time in Module 6 looking at confidence intervals, so at that point I'm going to give you more code in R as well as code in SAS, but for this set of notes we're just going to look at this specific type of interval in R. So here we fit those confidence intervals for each of these 4 different potential models, and here's what that output would look like. So the confidence intervals for the slope of the effect of age on the linear predictors for dying, so again we're going to look at dying, not surviving, are going to be the following. And so to find these, we're going to use fit 4 and fit 5. We could use one of the single fits, but it would just be more complicated. So it's easier to fit the fit that we want and then pull the confidence interval from that. So let's look at what we've got here. So for the first one, we want to find the interval for males that died. So let's go look at fit 4 and see what that gives us. So notice that fit 4 model died, and here it has female as the explanatory variable. So why do we want fit 4 when we want to find the confidence intervals for males? The reason for this is to remember that whenever we fit this, female is the 1, and for this particular model, male is the base case. So since male is the base case, this is going to be when male is equal, this is going to be when female is equal to 0. And so what that means, if we think in terms of our model, is since male is the base case, we're going to have that age is for male. Similar, if we look at the females, we want to use fit 5. And so if we go and look at fit 5, notice fit 5 is also fit where died is the response, but here we're going to use the one that it's age by male, and the reason for that is in this case, female is the base case. And this occurs when male is equal to 0. So again, remember that when the explanatory variable is equal to 0, that's when the interaction term drops off, and you're just left with age in the model. And so that's why we want to use these for these confidence intervals. Okay, so here's the corresponding confidence intervals, and then to find the confidence interval for the odds ratios of dying, again with a change in 10 years, all we have to do is then transform these by taking e to the power of the endpoint multiplied by the number of years we're interested in. If we wanted it just for the single year, you would just have that as 1. For a 10 year, we have a 10 here. You could do for 20, you'd have a 20 there. Hypothesis tests of odds ratios, for that matter, and probabilities are directly equivalent to the test of regression coefficients, and you end up with all the following are equivalent. So again, we can look at an example here. Suppose that we wanted to do a test of age given that the subject is male, and we wanted to see if that was equal to 0. So here, when we're going to model failing to survive, so again, we're going to model die here, we're going to end up with the following estimates. So let's see where these values are coming from. So again, we're interested in age given that the subject is male. The easiest model to get this from is going to be from fit 4. So if we go up to fit 4, remember this value of negative 0.3248. If we go up to fit 4, notice that that value is right here. Oops, sorry, I'm in the wrong spot here. We want to go, we can't find it here. If you go back and you look at where you fit these values in module 5.1, you'll find that that was the same estimate that we got, and you can find that from the fit 4. And then you've got the standard error of the estimate, and there you get your test statistic, and you can find the p-value by comparing to a normal distribution. And you could do something very similar with females. Now it ends up that these tests are relatively low powered because there are only 45 subjects, hence relatively high p-values despite the large estimated effects. And this phenomenon was apparent from the wide confidence intervals as well. And then I just paused and I went back and looked. If you go back, we actually do have these values in this note set. Have a look at page 6. So if we go up to page 6, I just didn't go far enough earlier. Here is the output that you want. And so notice here is where you're going to find that negative 0.03248 and that standard error of 0.03527. All right, so then just kind of a last note here. This is not the only way, and indeed it's not even the best way to approach inference for GLMs. The approach we have discussed today is what's called the Wald approach, and so it's after the statistician Abram Wald. This approach, however, is based on the approximation to the likelihood of beta hat and does not necessarily provide accurate information about the value of beta far from beta hat. So in the next module, we're going to discuss an alternative approach to testing and constructing confidence intervals based on likelihood ratios and see that it suffers less from this approximation problem. And this is why in this note set, I'm just giving you that limited R code to be able to produce these walled intervals. And I haven't provided the SAS code. And again, that's because we're going to discuss this in much more detail in the next set of notes.